Hey guys.
Good morning, good afternoon, good evening, where you are. I'm Nabih Cherradi from Desert Technologies as a company and president of SOLARUNITED, and I'm very glad and honored to moderate that webinar about the large wafer. Bigger, is it better? I think that nobody would expect a year ago in the early 2090s that the large wafer will dominate and will go that fast. And I was, with my previous experience in the equipment, what shall I turn off the camera?
No, that message was for Monica. I'm sorry.
Ah, okay. So what I couldn't expect that the increase and the changes of that paradigm of size of the wafer will go that fast. And today we can see that the size went crescendo from 166, 161, 166, and today it seems that the reference is 182 mm. This, of course,
notification.
Okay. So they will give you they will just
hello? And nobody can expect that that size will dominate, as I said, but it's obvious that through the size, we have been, since I would say solar was introduced into the market in the mid of 90s and early of, and then take off in the mid of 2000, we're mainly focused on how to reduce the cost through increasing the efficiency, reducing the gram per watt used, and so on. But at that time, no one started thinking about larger size of the wafers. Today, the large size seems to be very obvious. It's by increasing the size of the wafer, we can have much more watt. And then we can have, I would say, less BOS needed, cables, inverters, and all these things. And this, of course, toward the cost reduction. However, I would say, as usual, the opportunities will have also certain, I would say, challenges. I think that through that webinar with our prestigious speakers from different companies with their large experience, because we are very lucky today to have, I would say, and forgive me guys if I say, a dinosaur of the business of the solar industry are with us, when it means that the large experience, and we're gonna benefit out of their experience through the presentation that they will be giving to us. I think that without delay, we're gonna start our presentation, and we're gonna start with Dr. Markus Fischer from ITRPV. and he's gonna give us a large view about the wafer and the markets and what's going on, and then we go through Carsten, and then we'll Dr. Lee, and we'll see with Anis if he join us, because normally he should be with us also. And then after that, we'll Gaetan will give us kind of view about the large wafer and the challenges in terms of what is going to introduce into the equipment and the manufacturing, and we'll end up with a panel discussion. So without delay, please, Markus, the floor is yours.
Yeah, thank you very much. So now I try to share my screen. Can you see my screen? Okay. So I want to thank you very much, Nabih, for this kind introduction. So I want to give you a summary about the hottest findings of the ITRPV. And this will be the 12th edition. So some figures are preliminary and others are quite well known. So thank you very much. And so let's start. So outline of my presentation is here. First, a brief status about ITRPV learning curve and the trends in material and cell technology, especially some focus on the wafer size, by sure. And then I will show something about wafer and module format trends and close with an outlook. Okay. So quick review on the last year. So 2020, the expectation were so that we will become or will have gotten less output than in the former years, but finally what we found, so our preliminary figures are about 136 gigawatt peak were shipped of modules. So this is a slight increase compared to the last year, to 2019. And what we also found is the average price was decreasing. So the price learning continues with $0.21 per watt peak. So 21 cents. So this is quite interesting figure. I will also explain how we found this. Then this volume shipments overall come to overall shipments until 1976 to close to 800 gigawatt peak, and installation is about 760 gigawatt peak. Yeah, this is what we see and what we found. Yeah, production capacity still very high, and the trend is increasing. So end of last year, we see 270 gigawatt peak installed, and 93% of this is crystalline silicon based. Sure, crystalline silicon is the backbone of PV, and that's why we also discuss here with the ITRPV, especially silicon parameters. So putting these figures in the learning curve, we see continued learning rate over the years, 23.9%. And if you look here, especially on the years 2006 to 2020, we come to an accelerated learning with about 40%. Overall, the summary for last year, slide shipment increase in 2020 despite the crisis in COVID. So we have a significant change in module concepts and size. This is what we see. And PERC is still the PV workhorse. And we see also a price premium for new formats. Price learning nevertheless continues. So this is what we see here, the trend about the different materials for our crystalline silicon modules. So the trend regarding P-type mono is unchanged, and so casting material is expected to get more and more phased out. So still a small share will remain. But anyhow, so mainstream is P-type, P-type mono, and then we see also appearing mono N-type. So this is what we see. And here I mentioned here the average price we found in end of 2020, 21 cent. So this is a calculation assuming here average prices at the year end for monosilicon standard modules of $20 per watt peak, multicrystalline much less, 18 cents per watt peak, and then we see a premium, a price, quite higher price for new formats. So about 23 cents for new format modules, and bifacial with about 30 cents per watt peak. And so we could calculate here this value. So what we see in the trend, the mono standard pricing is dominating the average pricing. So and now to the different cell technologies. So what we see, what I mentioned before here, this P-type mono. So dominating, we see that PERC and top cell concepts, so all concepts with diffused PN junction, so are dominating, and PERC is the workhorse of current technologies that we see. So BSF is about to be phased out, so only 15% share in 2020 and will disappear within the next years. And I marked here this region, so all these technologies, including this upcoming heterojunction, are technologies that are capable of bifaciality, and bifacial cell concepts will gain more and more share in the market. So overall, we see for this PERC more than 65%, and here heterojunction is getting more and more share. So now let's look here on the market shares regarding the current mainstream technologies for P-mono and for mono PERC and others. So for this mono diffused or cell concepts with diffused junction, we see PERC will stay the workhorse, And we see here upcoming this new technologies on N-type, so with passivated contacts, and here also multicrystalline CESI PERC, so is about to be disappear. So this is what we see, and here regarding the bifaciality, we see here more and more modules, more and more bifacial modules will appear, and we see also that the cells can be used in both type of modules. These bifacial cells will partially be used in monofacial modules and can be used in pure bifacial modules. So this trend, bifacial modules will get more and more market share, and the cells can be dual use. So this is also a big advantage of the cell technologies. So now the most important thing we want to discuss today is the module format trend. I summarized here what happened in the past. Nabih, you mentioned this in beginning of 2019. So there was some rumor about this new format. So now in 2020, we saw that this module formats diversify. So only remember Q cells was really the founder here for the 6-inch format. But now we discuss here this M6 format, M10 and 12. And we see that probably here the M2 is disappearing, or disappears completely, and the new formats will dominating. And this is what we found here in the ITRPV survey. So these are the figures we have so far. So M2 is no playing any role anymore. So we have here this G1 format. G1 format has currently still considerable market share, mainly here with a full square product. And what we see M6, and this is also the title of our conference here, of our workshop, M6 is increasing market share. And so in 2021, we expect that M6 is having the main market share. But we see here this new formats M10 and M12, so they will appear soon in larger and larger quantities. So all the new factories are ready to produce M10 and also capable of producing and using M12 format. So this is what we see. And yeah, it's also interesting to see the discussion about full square. So we had in the past also some products that were full square. Finally, this was too expensive, and so pseudo square was the mainstream. We see here with the G1. So there we had yeah, a lot of full square. So then we see here M6 is yeah, mainly with again pseudo square, also for M10, but for M12, and this is really surprising. We see here this full square format as yeah, as a mostly used format currently. So, and what is the trend? So M6 is currently over the next years expected to play a role, and M10 and M12 are expected to dominate in the next yeah, in the next future. And yeah, what is this for upgrading existing lines? So there we need concepts, what can be done with M6, but for M10, sure, we need completely new lines and new tools for working with this large formats. Regarding thickness, we also, as always, looked here at the thickness trend, and there we see in 2021, we expect that everything will have quite similar thickness of 160 microns. But over the next years, the expectation is that M6 and G1 has yeah, slightly higher potential for reduction, and M10 and 12 is expected to come down to 150 microns. So. And now also interesting, what is, especially with this new cell formats, what is the outcome in the modules? In general, we see that with the different form factors, here's a 120 half cell, so there is a quite yeah, constant share. So this is mainly used, mainly used for rooftop applications. And here for the power plant applications, we have the larger formats, but we also see here, so maybe some new formats appearing. But what is the most interesting thing is what will be the outcome here about the module area for the rooftops. So rooftops are have always limited areas. So in there, this is a classical 120 half cell format. So the expectation is that the mainstream will be within 1.7 to 1.8 square meters. And yeah, so, but also modules larger than 1.8 square meters appear. And for the power plant application, so Nabih, you mentioned this, so with larger modules, we can really optimize the BOS cost of a system. So there, the mainstream currently is yeah, shifting from the pure 2 square meter to 2.2 square meter and beyond. So, and then we will see also there is expectations that 3 square meter modules will appear. So this is what will be very exciting, but finally we have to handle also these modules, and we will see what finally will be the format of the future. And it is also for end customers, it's quite yeah, challenging to evaluate because most of the power increase of the modules is coming not from the cell technology, but from slightly part from module technology, but mainly from the module size and from the wafer size. So, and then we also had again in this 12th edition an outlook about yeah, the current situation regarding the efficiency learning rate. If we consider only a price reduction from 2010 to now by efficiency learning and by per piece learning. So we see here over the last year, especially the per piece learning was a little bit delayed. Yeah. So this was a negative learning. So it was per piece. So that means if you consider the price, so it was more expensive if you consider only the piece cost and piece price. So this is mainly our conclusion due to the larger modules. So you have also to look for special materials and so, but nevertheless, the combination with between efficiency increase and continuous cost reduction per piece, this will be also the formula for the future. And this is what we will see to continue this learning. And we will see that this new cell dimensions will be implemented also for the new technologies. Upcoming new cell technologies will accelerate efficiency learning, and so we have to combine this efficiency learning and new processes, complex processes, with the big challenge of continuing the also per piece learning. And so PV industry takes this challenge, and we as ITRPV will also show some ways how to realize this. So I'm now at the end of my presentation. Thank you very much for your interest. So this presentation will be available so latest end of April, so when we launch the full 12th edition. So thank you very much, and now Nabih, questions.
Okay. Thank you so much. Ola, there's an can somebody switch off, because I hear echo. Hello, yes. Thank you so much, Markus, for your updates presentation and trend of the markets and the challenges. It's extremely interesting to see exactly how the market is going, and especially regarding the wafer size. We used to always talk about the efficiency improvements, but I would say nowadays the question is more and more dominated by the wafer size. And this is represent a big challenges in terms of not until the wafering is not a big changes or a big evolution, I would say. However, starting from the cell and so on, this where there are challenges, especially if we start, I would say, manipulating large wafers and thin with thin thickness. You mentioned about 150 micron. I wonder about how is going to be the yield with M12, for instance. It's something which is extremely delicate, because even if today the slicing is done by diamond wire, where we have less surface tension between wafers and singulation of the wafers is getting easier than with the slurry. It's still somehow a big challenges in terms of the yield. But I'm pretty sure also, again, I'd say opportunities and development is created by the necessity, and it's gonna be the case. I think, as I know that Markus, you should leave us in 15 minutes, 20 minutes from now. Normally the questions are at the end, but I would like to ask you at least one or two questions that comes here from the audience, is regarding that you show the price of 30 cents for the bifacial modules. Why at the most it seems to be around 4 cents price increase. So can you explain these numbers, please?
So I took, or we took in the analysis this price data from public available pricing table. So for PV Insights, perhaps. So this is what we took, and there we took the spot market prices. So this is not for special contracts or so, and there we found really that there is an average price for this bifacial modules of 30 cents per watt peak, and for this larger modules there was also a price premium compared to the standard module sizes. This was interesting to see, and if we would have considered only standard mono and multi, so the price decrease was much more tremendous. So but this is the current fact, and the power plant builders, so they obviously are willing to pay also a little bit more, and this pays off with optimized BOS and finally the LCOE. So this is the final figure. This will be the most argument, and then you can also see here some higher prices.
Okay, thank you. Another question is, because you mentioned in your presentation that starting from M10 and 12, the lines will be obsolete. This is a huge challenge, because how are we going to answer the market demand if the lines start to be obsolete and the replacement is not easy? We all know that the equipment manufacturer, they are not too many, they cannot deliver gigawatts, hundreds of gigawatts yearly to the customer. Are, of course, there are a lot of announcements of new lines, new equipment and all these things, but to replace the existing, because if we look today about the overall installed capacity or running capacity, maybe it's around something which is, roughly speaking, around 200 gigawatt. So in that average, I would say. Some people will say that no, it's only 180. Others, they will say no, it's 220. Let's say it's 200 gigawatt, roughly speaking. And even in this 200 gigawatt, I am pretty sure that there are a lot of equipment which are obsolete. So how do you see the equipment manufacturer market going on?
So what I currently see is in the market that there is or continued investment in new capacities, and so announcements call for up to end of this year more than 350 gigawatt installed capacity. So, and this is what I see. So that means within the last year and this year, so more than 150 gigawatt will go online, go active, and all this capacity. This is my feeling. So this is what I also saw in China. So last year not, but in 2019 even, when I was last time in China, I saw that new lines are preparing for this large wafers. So for me, the challenge is now who can really keep pace with this tremendous increase of capacity and with this investment in new tools. And as we found here with this analysis, so for the current capacity, you still have the possibility for G1 format. This is a 158. And yes, so there is an intermediate format, this is M4 format. So there is also a possibility to maintain the usage of this depreciated factories. Yeah, so this is the best factory is a depreciated factory, and this is now the challenge. Yeah, so how to handle with the depreciated factories this new formats, and this is a challenge also the equipment manufacturers have to face. Maybe in some points we can adapt, in some points you have to replace, and this is now the engineer's question to keep on your very efficient production. So, and for new investments, so then you have only the choice to be capable of 10 and 12. So this is what we see, and I'm not worrying about the capacity. So I'm worrying about meeting here all the changes regarding here equipment efficiency and overall equipment efficiency also with this large formats. So this is a big challenge. You mentioned this with the wafer thickness. When we started at Q-cells, when I started with Q-cells, so we stopped the 8-inch wafers. So we had, and we still have these wafers. So, but they were 300 microns thick, even thicker, and they are so brittle, so they could not be handled very stable. This changed completely, and this is really big progress in the crystallization and the wafering process. So, and the challenge is to have the same productivity with the new tools like with the old.
I understand that. Just for the memory, I do remember that when I used to work with HCT, we made a demo cut that QSERs, that it was in the early 2000s, at 120 micron wafers. We cut for them, and they made that was in early 2000, just to demonstrate that it's feasible. It's feasible, but of course, that's the yield is another matter. Just last question. Do you see in that opportunity of the move of now and the standard large wafer, and that we need probably for a lot of manufacturer a new equipment, a new line, a move, one opportunity to switch completely to another technology, like for instance heterojunction, that we need completely full cell line?
There are always opportunities, yeah. So, but switching to a new format with a new technology, yeah. So from the beginning, so semiconductor industry taught us how to handle this, yeah. So they switched. They had a very hard learning with switching from 6-inch to 8-inch due to converting the same processes. And so for the 300 millimeters, there was a learning. So they implemented the new processes directly at the 300 millimeter. So the challenge for heterojunction would be to have it directly on M12. So I think the PERC process itself is very robust and can be transferred. So this is what we see in the market currently, can be transferred with the existing process technologies quite smooth to this new formats. And that's why I'm quite sure that PERC will stay here for the mainstream and for the current workforce, the process of choice. But here for new equipments, yeah, you have really to consider, make it capable, especially here also for the new formats, and then you have to meet the challenge of uniformity and also here yield and product performance. This is right, yeah. And yeah, chance for new greenfield plants as always.
Okay. So thank you so much, Markus. It's always a pleasure to exchange with you and discuss with you. I always learn a lot. Thank you so much.
You are welcome. Thank you.
And we'll continue now with our next speaker. Is Carsten from Norsun, and his presentation will be entitled Changing Wafer Size. And this is another new challenges that continue to explore that new, I would say, jump. Please, Carsten.
Yes, thank you, and welcome everybody. My name is Carsten Rohr from Norsun, and I'm also Vice Chair of the European Solar Manufacturing Council. I'll give you a little overview about Norsun, and then we'll go into the details about the changing wafer size. So just a quick overview. Norsun is in manufacturing of ingots and wafers. This is this part of the value chain for focusing on premium products, high efficiency, low CO2 footprints. And we started in production in 2008, so we have a long track record serving the top tier 1 solar cell manufacturers. We are currently expanding our capacity to 1 gigawatt, and located in Årdal, which is a little town at the end of the fjord in the west coast of Norway. There we have the advantage of being powered by hydroelectricity. And that, of course, provides low CO2 footprints, and we also have readily available cooling water from a nearby glacier, so that also reduces electricity consumption. We have currently 230 employees, and just as an overview, our owners are the Norwegian Norsun Climate Invest, which is a governmental investment fund to facilitate the green transition. ABN AMRO, the Dutch bank, through the Energy Transition Fund, and Scatec, the original owner and founder throughout Bjørset, still one of the major shareholders. So I mentioned the CO2 footprint, and that's it's been rising in importance in recent years as one important factor, and also where we have a competitive advantage, here illustrated on the left-hand side in the French system. The French tender system, as most of you know, have an explicit CO2 footprint value as part of their tender system. And here in the graph is shown the wafer, including the polysilicon and ingot, and Chinese, typical standard Chinese, with a high CO2 footprint compared to Norsun with a life cycle assessment, only 10 grams per watt for the ingot and wafer production. So extremely low. And as I mentioned, that's based on the hydropower that we have, the reduced electricity consumption through the cooling water availability, of also our prime focus, which has been the high efficiency segment, which also reduces, of course, the silicon per watt, and therefore also the CO2 footprint per watt. In addition, highly efficient recycling process of silicon contributing, and one important element in addition is the sawing of thin wafers with thin diamond wire. So thin wafers obviously reduce material consumption, and thin wire reduces the kerf loss and waste. So those are that's what we are known for, high efficiency and low carbon footprint wafers from Norsun. Demand has been strong, and we have had small capacity, so we are starting expansion. This is the first phase to 1 gigawatt that we are doing right now, installing larger pullers, 28-inch and larger. Importantly also, control system and safety features. Maybe not so known, but this is potentially a dangerous process with very high temperatures and water close by, and there are accidents happening regularly, including with fatalities. So that is, of course, something that we cannot allow, and so we have very good additional safety features. In addition to pulling, then the shaping area, where we have new equipment, highly automated shaping center. So the ingot goes in on one end and comes out ready measured block for sawing. On the sawing side, we have top end high capacity wafer saws, and I'll explain a bit more later on, which then in the last part of the process, the cleaning, which is also a fully automated new cleaning line with including automatic packing at the end. So the pullers, the large pullers, they are, of course, they are suitable for all wafer formats up to G12 as possible. However, the other equipment, that's more limited due to the design of the equipment. So in particular, the saws are limited to M6 format for this, and I'll get back to that, as I mentioned. This is just the first phase where we're expanding right now, but we want to continue and grow further. So we are planning a next stage, growing to a total of 4 to 5 gigawatts at the current location to achieve scale, of course, and also to reduce costs. That's further expansion that will be compatible with the larger formats of M10 and G12. We just started the pre-project for that. We have land already available directly adjacent to the current factory and also a nearby industrial area. So the plan is to start the financing activities later this year and then ramping in 2023. Well, that's essentially being based on technology and innovation. I mentioned already quite a few of those. Highest ingot productivity, highest material quality, of course, and safe operations, also quite very important. The adaptive controls with a lot of artificial intelligence, and these are developed by us. In terms of wafer, high capacity is of course important. Going further in terms of wire diameter reduction, as well as thinner wafers. Recycling and reuse is important too. That's not just for environmental reasons, but of course as well, but it also reduces costs, of course. And automation is clearly important, in particular in a high labor cost country as Norway. This is crucial. And automation is not just for reduction of labor costs, but also for increasing process stability and quality. So in terms of wafer size development, we've heard already some of it. We started when we started production in Norsun in 2008. All of it was 125 millimeter. That was the standard at the time, and that was up till around about 2010. Here illustrated is the side length and the diameter on this graph, and the to scale illustration of the wafer size for the different formats. Initially, the wafer size was pushed up in terms of the diameter to fill more of the pseudo square corners. And then, of course, the big steps in terms of area come with the increase in side length. And around 2013, the standard was the M0, or the 6-inch M0 format with a 200 millimeter ingot size and 156 millimeter side length. And then there were not much happened until the M2 size came in 15-16, slightly bigger, slightly larger side length and diameter increase. And then the next few years were incremental increases. The M3 slightly larger, just pushing the limits on both dimensions. And then the G1 came with a larger diameter, full square, and the M4, which went the other direction, pushing the side length instead of the diameter, a similar area actually. Until 18-19, where clearly it was about how can we continue, and some of the drivers was to increase the module power rather than because it was getting towards getting more difficult to increase the efficiency rapidly. So the larger sizes were pushed, and then the M6 format came in 2019. And then it went very quickly. In the middle of 2019, TZS announced the G12 format, and shortly after, LONGi came with the M10 format, significantly larger wafers. So just in terms of the area, that's a bit of a question. How do you square the circle, right? The ingots, they are round and the solar panels are square. So we need to find some sort of compromise. And some of you may remember all the way back to the beginnings when the wafer size was even smaller. There were round wafers to start with, essentially wafers from the semicon industry. And that was, of course, the optimal wafer size compared to the ingot. Then the wafer needs to go into a square panel, and with the round wafers you can arrange them in hexagonal formats, but then you have problems with the edges and corners. So it's better to fill the module with squares, and so the pseudo square came, and as I mentioned already, pushing the corners means increasing the diameter. By doing that, as you can see, you have a lot of waste, increasing volume of silicon that you need to recycle and remelt. And in addition to the side cuts that are getting bigger, also the top and the tail of the ingot is increasing with larger diameters. So the further out you get diminishing returns for increasing the diameter. The last bit, you need to add a lot of, grow a lot of extra material for getting very little extra in terms of area. And some of the area even that you're trying to fill is not completely dead either. So it's not 100% gain if you do so, because you have reflections from that area as well. So that's just an overview of the more detailed numbers of the different sizes. But clearly the biggest jump was going from the 5-inch to the 6-inch in terms of area, and then the incremental increases that I mentioned until we get from the M6 to the M10 with a 20% increase, or from M6 to G12 with a more than 60% increase. So those are, of course, substantial. Just a small illustration, if you look in terms of filling the corner from the M3, which is a pseudo square, you can see there's a 25,000 is the area, going to a G1, which is the full square. You just increase the diameter accordingly, and you gain only 0.7% of area, while you actually have to increase more than 10% of the silicon material that you need to grow in a larger diameter. The driving forces, I'll get back to ingot and wafer, but are mainly further downstream, cell and module production in particular, where the cell line throughput is driven mainly by piece per hour. So if you have a larger piece, then of course you get more through, you increase your watt. So that's a big driver for the cell process, of course, and for the module, similarly, you have increasing the module size, and it's largely per piece, and so you increase the watt peak that you produce. Another important factor, maybe not to underestimate, is the marketing. There is a competition to reach the highest watt peak per module, even though the efficiency isn't really necessarily increasing, but you make the module bigger and bigger and have a higher watt per module watt rating. At the end of the day, what matters really is the LCOE, the levelized cost of electricity. So there are the benefits in the balance of system with larger modules. The rest of the system has a similar cost, and therefore you reduce the cost per installed watt peak and reduce the levelized cost of electricity. In terms of the ingot and wafer process, there are also some fundamental advantages of going to larger wafers. Larger diameter increases actually the pull speed. You can have a higher pull speed in terms of kilos per time unit. So that means you can actually, and kilos is in the end equivalent to a larger area. So it's throughput in the end per watt that's increased. So, but also it requires that you can increase the crucible size to maintain the ingot length, meaning that you need, of course, more material for larger wafers that needs to have space in the crucible, and that the puller needs to be able to handle both the diameter and also the increased weight. In terms of shaping, it's larger wafer area means less area to shape, and therefore fewer blocks to handle, although those blocks will become heavier, of course. Wafer sawing, there are also some advantages. The cutting time is reduced in terms of the area, because it gets less than the area. So you increase the throughput per area. And you also have, of course, you have per each pit stop, per each run, you produce a larger area. So that also helps. In terms of the wafer line, the cleaning line, you have, first of all, fewer wafers, fewer wafer pieces per wafer area, and that means a higher productivity because it largely goes per piece in terms of singulators, and in particular for the batch tool, for the inspection, for the packaging. So those are the advantages, but you also have some drawbacks and challenges. In particular for ingot pulling, this is that you need to increase the diameter also of the crucible. You need to have roughly 3 times the diameter, crucible diameter compared to the ingot diameter to have a stable process, and otherwise the crystal rotation will have a strong impact on the melt flow, and therefore stability. Also variability or variations in the crucible diameter has an increasingly big impact on the growth, and also the pull speed is related to the ratio of crucible to ingot diameter. So that means you need to push up the crucible diameter. That's the illustration with the crystal diameter and the crucible diameter going from the original 20-inch for the 125 millimeter wafers to 28 for the larger formats, and actually to be in a more ideal situation, you go to 32-inch crucibles for the G12 format. Going to larger crucibles, however, has its disadvantages. Clearly, there's much stronger natural convection in the melts, and there's less stability, therefore, and you will struggle with more structure losses. So that's a challenge. And when you do have a structure loss, which does happen from time to time, then that means for a larger diameter, you need to cut away the same diameter. So if you have a large diameter, you need to cut more than if you have a small diameter, you cut less. So the yield will also reduce because of that. And then you also have some issues in terms of getting the latent heat out of the ingot when it is so big, which may limit potentially some of the pull speed. Some may say, okay, but Semicon does that all the time. They do 300 millimeter, yes, but it's not quite comparable. Of course, they have quite different regimes. They're not in producing as much as possible, and most importantly, they have superconducting magnets to stabilize the melt, which would be prohibitively expensive for PV. In terms of wafer sawing, there are also some fundamental challenges here, and we have heard some indication already. Here's an illustration of a wafer saw, how it looks like inside, with the wire guide rollers here. The wire is going around and arranged in a web, in a wire web. And this is a silicon piece. It's already halfway through the wire web. So below it's half wafer, and on above is still the block. And if you look at it from the side as a schematic, that's the block being pushed through the web, and so the wafer is developing while the wire is cutting through the piece. Until fairly recently, there has been a lot of improvement actually in terms of the sawing technology and the stability by bringing the wire guide rollers closer together to have a more stable wire web, increasing the tension and thereby being able to cut faster and to reduce the thickness of the wire and the wafer. But of course, if we are now increasing the wafer size, we need to increase the distance between the wire guide rollers again to accommodate the larger piece. So that means that the unsupported wire between the wire guides becomes longer and therefore less stable, which means that the wire tension becomes less, and which creates issues. And to compensate, you may need to actually increase the core wire thickness again, which would then have a higher kerf loss. And thereby lower wafers, which has a big impact on the cost again. So and on the throughput. In addition to that, you have the yield question. That the wafer, much bigger wafers are more susceptible to breakage, of course, and typical today is 0.5 to 1% yield loss of the larger M10, M12 compared to M6, and that's per piece. So actually per area, this is of course even bigger, and that's big. That's wafers that gone through all the process you destroy at the end is obviously also important, significant cost effect. It's also more prone to stains, a larger area, because it's more difficult to get in between the wafers to clean them. And you may have more total thickness variation issues because of the tension, for example, in the wire. So one way to compensate at least some of that is to go to thicker wafers again, but that would, of course, increase the costs substantially, and in particular when polysilicon costs are increasing, that's important. So overall, are larger wafers better? Yeah, maybe. For ingots, it's a marginal case, maybe a little bit better. Yes, for wafer, currently, no, it's actually a negative effect, especially because of the yield. What is critical, and that's critical for going forward as well, is the process control and improving yields. That's if you have a higher yield loss, of course, then the case is negative. So the gains are mainly further downstream on the cell and mostly on the ingot and system, on the module and system level. But having said that, there is maybe actually a potential for greater gains if we focus more on thinner wafers rather than larger wafers. And that is particular of interest maybe for some of the technologies, the high efficiency technologies like heterojunction and IBC, which are more suitable for thinner wafers. And so that would of course reduce the cost per watt peak. So larger wafers per se are not necessarily significantly better or cheaper per watt peak, of course, always. But it's the system aspects that are most relevant. So the optimizing the whole system, including the efficiency, the cell efficiency, but also system configuration and design, the transport issues, logistics, module size in containers and balance of system to optimize those, that all those elements fit together well, including inverters and everything else. Bankability is always an issue. That's the last point, and with a question mark, with a new technology and new wafer sizes, new module sizes, there may be more questions about micro cracks in larger wafers. So that's just one of the elements. That's a question that will certainly be addressed over time. So that was a quick overview. Now, of course, I'm happy to answer any questions and participate in the discussion.
Thank you so much, Carsten. And I would like to thank you twice because, you know, through your presentation, I went 30 years back in my life. It reminds me. It reminds me of Versit sitting together in front of the wire saw at Glenfjord.
Yes.
That was the start of all that, the Norsun and Scan Wafer that turns to become RSC afterwards. It's extremely interesting, and it's extremely the point that I always mention since, I would say, years when we were, I would say, moving. Talking about thin-wafer at first and then large wafer. And this is a huge trade-off between going larger or going thinner in terms of manipulation. I would say that the machines can handle that without any problem. Pullers can handle that. We know that from semiconductor industry, 12-inch, even now 16-inch is not a big deal. How wire saw we cut into, I think it's 1996. We made a demo for Deutsche Solar in that time with 210 ingots block, and we cut it at 50 micron. But I cannot tell you the yield; it was a disaster.
Exactly.
That's always, and when we talk about, of course, that size is automatically high power. So we can think about low BOS, less BOS, decreasing the cost, but what about the yield at the end of the day? And that also was the race. If we remember when the mid-2000, when the price of polysilicon starts going up, a lot of manufacturers, especially in Japan in that time, they start looking for thin wafers, and they cut sharp when at that time at 150 micron wafers, but 3 months later they returned to 220, which was the standard at that time. So it's a lot of things to be done, to be discussed to your presentation, but I would rather, if you don't mind, to leave the discussion and the questions at the end of all the presentations. And we're gonna move, because you give us also the link to Dr. Anis Jawi from INES, who is gonna make a presentation regarding large versus thin. And it's exactly in the heart of our discussion. So Anis, please, the floor is yours.
Thank you very much, Nabih. And I would say there is a lot which have been said, and thank you, Carsten, for the rich presentation, which make my life a little bit easier, by the way. And I will try to share my screen. Not this one. I think you can see my screen, Nabih?
Yes.
Good. Then it's as everybody knows, this huge move for large wafer. It was very surprising for a lot of us. And by the way, for PV, it's more and more surprises are coming very often. And for the moment, we are not growing this internally in our institute. We are getting a lot of wafer from the market. And we hope that the next coming month, we can really come back with more deeply and technical presentation about this. Let me move this to a side. Okay, like this. So it's to start. I introduce the company. I think a lot of people knows that our mother company is
Anis, we don't see the one slide. We see now a myriad of slides. So we see all the slides. We don't see one slide.
Sorry, then I will repeat again.
Anis, I'm sorry for interrupting. Just go ahead and put it in presentation mode.
So this is like this, it's okay?
That's better,
Yeah.
But if you hit on the bottom, yes, push that. Oh, okay. This should be okay.
Now it's okay? Okay, good. Then let me, then as a general overview, and we are really, we were pushing since a long time thin wafer because we have used a lot of economic modeling, and we have seen that increasing the wafer efficiency, it's really a good thing to do, but also reducing the wafer thickness can bring a lot in terms of cost reduction while keeping, I would say, the efficiency at the same level. Two quick slides to introduce the company. We belong to CEA as a mother company, and we belong to the energy division, and we are much known as under the name of INES when we are gathering development of material and cells till the integration of the solar PV system, and developing a lot of grid integration and diagnostic and energy management system. And we are surrounded with more than 150 industrial partners. I would say we recently get our new website, so please do not hesitate to go there to find the new information about us. And we are happy to get your feedback. And this, I have shown this slide a little bit earlier. We were impressed in 2020 by the transformation and new era coming from oil majors toward renewable. And we can see that a lot of names are putting a lot of billion, and we are starting a new era when Carsten were mentioning ESMC, when we are fighting to get, let's say, industry back to Europe, because we are moving to a new phase. And this move, I would say, going from M2 or M4 wafer to M6 and to more M10 and M12, it's really, there is no need to upgrade the existing line, and then you need the new lines, and our strategy at the European level fits with this. If we go back to the talk of today, I would say everything is becoming big when it comes to PV. So power plants in the past, they were in the range of a megawatt. So today it's in the range of a few hundred of megawatt. And in different location, then the PV module is following. When it comes to PV, it's all the time question of surface. And trying to get more power with a reasonable price and the right quality, and eco-design module is of course coming just behind this. So, which is impressive that we are a market which is absorbing 150 to 160 gigawatt, and with the production capacity, it's almost above 250 gigawatt worldwide. And we are at the institute pushing different cell technology and with a lot of communication about heterojunction in addition to passivated contact. If we go back to the large wafers, Carsten were mentioning a lot of I would say precision and details about the growth. Having a strong background in the growth technology and having also we were here at Ines growing both CZ, cast mono, and mono-like at the same time, we were seeing that in terms of technology, while going from M6 or M2 to M10, M12, following the microelectronic industry, there will be a lot, I would say, of aggressive new challenges for those large wafers. Because in the past, once you moved from 5-inch to 6-inch, we were at least at a very low efficiency compared to what silicon could offer. We were in the range of 15 to 17% efficiency. And after that, it was the growth 0.6 per year, roughly, to reach 20% for I would say, for standard technology. So today, we are at the same time going for bigger wafer, having a capacity in the market or even production in the market for more than 190 gigawatt in 2021, about when it comes CZ or CCZ or successive Cherradi also. And at the same time, we are preparing those wafer to produce 24 and above. And when it goes to the PERC and PERC Plus, it's then 22% efficiency and above. So, and in the recent years, there was a lot of I would say, trade-off between multi and mono. And many times we said, yeah, multi will take it over. No, mono will take it over. I think in 2021, the figure, at least, this is based on a number. We have the player who announced this, and we have this listing also in a good order. We have seen that when it comes to multi, the main player like GCL, Canadian, and by the way, they are all Chinese who are manufacturing multi today. And it's really a limited number of actors for a very low capacity, which is 6 to 10 gigawatt, which is surprising because when we go to large wafer, then cast mono, you can cut whatever you want in it. But as I said at the beginning, we are moving to larger wafer, but this larger wafer will be combined with very high efficiency. And then after I will talk a little bit, this will be first point. What about growth technology for this? And there is a lot of challenges. Second part will be doping. We have seen that gallium is coming very quickly to take a market share compared to boron when it goes to P-type. And at the same time, we have seen that all this potential high efficiency technology, they are linked to N-type. And there is a lot of prediction for a very bright future for N-type. But at the moment, the number that we have, it's roughly 7 to 10 gigawatt market share in 2021. So coming from having this background from crystallography, we know that the growth rate and the quality are very, very linked. And adding this growth rate to the large ingot size, and whatever is successive or CCZ or CZ, there is a huge challenge. And with the furnace itself, related to the metallic impurity and the crucible, the quartz crucible, when it comes to oxygen contamination. And we have seen also at the same time, we link it directly, those oxygen problem, those dislocation, if there is any, and they are completely linked to a simple degradation of the efficiency of the cells. I will talk a little bit briefly about the price because I just picked up the number coming from Longi at the end of February. And the latest point, which for us will be really main challenge, is the strategy of recycling. Getting big ingots, and of course we are losing more silicon when we are getting the wafer. And we have seen that we are seeing a numbers of a very aggressive recycling strategy I would say, linked also to the lower carbon footprint processes, which is very aggressive, and people are showing a huge number which is compatible that whatever you are making as a wafer size, this is not an issue if you know how to do it. If you go back to the same slide that was shown a little bit earlier by Carsten, we have seen a different move. This industry, there is a big lack of standard. For us, from the point of view of research and development, it's a little bit tough, because once we start focusing on M6 wafer and developing a lot of model about it, how it behaves when we try to combine it with high efficiency processes. So the industry moved in a few months to M10, M12, and there is a lot of announcement of a big manufacturing scale for those wafers. So we were seeing, I think everybody agrees that once you are getting for larger wafer, it's more power and it's less cabling, balance of system reduction, etc. But which was impressive also when we look to the price coming from Longi on February 26, and we see here we put the M2 wafer, $0.48 per piece, 170 micron. For the same thickness, the difference is really too small when we go to M6. And when we compare M6 to M10 or M2 to M10, we find somehow, even though the M10 wafer are thicker, so the price is still proportional. It's 17 to 18% more surface, 17 to 8% more power, more price, which means for the moment, even though we are still producing those wafers at lower scale compared to what we have on M2 and M6, we have seen the industry, it's controlling the prices. Is it realistic or is it done for a reason? I cannot answer. And I put here just a question mark. We hope that this is it, and we will be stabilizing this industry to focus for a dedicated wafer size, at least for a few years, in order really what we can bring some added value around those wafers. In the past, in 2005, like Nabih was mentioning this, in PV it's almost the same story. Old stories are coming, and where it's at the period when the industry moved from 5-inch to 6-inch, there was a lot of discussion moving from 6-inch to 2010 wafers. We started at that time having, I would say, YSO compatible with 210, and we were very active at the time. Multi was getting a big share of the market in 2005, and we tried solar cells at 2000 to 210. The wafer thickness at the time, it was 190 to 200 micron. And almost, I would say, when it comes to the cell processes at the R&D level, because we haven't processed, I would say, thousands and thousands of wafers, there is almost no big issue. There was just small issue to handle, like sticking of the wafer. Once we are the cleaning, then we have to space them more. Bending of the wafer, depending on their thickness. We were having also in the pre-clean and the clean process, we're having a lot of loss and sometimes breakage of the wafers. But I think between 2005 and 2021, 15 years later or 16 years later, the industry made a huge progress in order to know how this soft handling, how this soft processing is becoming a new word in the PV industry. Soft behind everything, because we have seen that while going through soft processing, soft cleaning and others, we are able to handle those wafer to reduce the breakage rate to very, very low rate. And we are not seeing any issue in order to go with this wafer size. And there is a lot of work which will be done when it goes to the wafering itself or the cleaning or even the processing. We were using a lot different solar cells processes, and I put on the title horizontal deposition processes. Like a technology like heterojunction, we are making deposition of the wafer on the top of a tray in a horizontal way, and this is when it comes to the PCVD, or when also it goes to the PVD, or when it goes to the metallization. We are not seeing any issue while processing recently M6 wafer. We are processing this in a lab mode, I would say, not with 2,400 wafer per hour, I would say, automated process. And the results, of course, we are getting efficiency a little bit lower to the standard that we have with M2, 0.5 to 0.8, a little bit below. But for this, I would say it's normal because we haven't tuned our process to get adapted for large wafers. So once again, we don't see any blocking point or anything that will really limit us to reach the same performance like what we have done in the past for M2 wafers. Here it's in one photo. You can see it. It's a little bit impressive. Cutting the wafer in two parts or in three or in more, depending on the module design. This also it's I would say helped a lot the large wafer to come in and to get their part immediately in the PV industry. If we are really handling more those large wafers, I think they will be getting a lot of issue at module assembling. And now I would say the question is more went to the module design. And we have seen that we went from one period when we were gaining +5 watt per year, once improving the efficiency. And while coming with those big wafer, we went immediately from the era of 400 watt per module. I'm talking about 60 cells to 450. And when it goes to 72 cells module, people today are talking about 600 watts. So this brings the industry in a very short time to a lot of watts per hour per square meter when it comes to the module. Interconnection of the cells, half cells or just ribbons or it's becoming a hot topic and we are taking care of it. I would say the negative point, Nabih, that I can mention today, it's our industry will be still missing the standard at different level, at the wafer level, at the cell technology level, at the module level, and this is a lot for one industry. And we will continue with adapted product for different application and different vendor and different markets, but it's not helping really to stabilize the whole thing. So if I try to summarize this in one slide, I would say we went out very quickly from the era when we are reaching 0.6% efficiency per year progress, and then we were stuck a little bit with the PERC and PERC plus limit at the 22, 23%. Maybe other colleagues, they said, yeah, we reached more, but this is not the question. And in the meantime, we forget the figure on the middle. We go immediately to the figure at the right level. We don't have a new technology able to be to get into the market while bringing 30% cell efficiency. We were talking about since years and years, but for the moment we don't have a tandem cell with a module which is bankable, that really people they can think about the manufacturing. And I can get my optimistic point of view. Let's say that this is coming in 4 to 5 years, and I'm really optimistic. In the meantime, there is a gap between both. And in this gap, there is new technology like heterojunction who are coming in very, very strongly, passivated contact or TOPCon N-type. And people, they really move it very quickly because the PV industry is very aggressive, and they find out that there is something to do with the module while bringing the cells larger. And this is more an innovation coming from the side of technology, and it went very, very quickly. And behind, it's linked to shingling, gapless, half cut size, how to cut the size and how to passivate those cells in order to keep them with the right performance. And this, what we have seen, I would say this between 2020 and a little bit earlier, and this will last, I would say, for 2021 and even 2022 in waiting for the next phase of PV with N-type solar cell processes and combined with a gigawatt scale production. Thank you for your attention. And this is what I can bring to the table as a general overview, waiting for a much more deep technical presentation, which will come with, I would say, with the next PV Sec and others. Thank you.
Thank you, Anis, for your presentation and overview from the ingot to the module, showing the opportunities and the challenges. Of course, that we went, I think that we took more than 10 years to move from 5-inch to 6-inch, but now we are witnessing in less than a year and a half, we went up to M10, M12 even. But we don't see all the situation today. We don't, I would say, measure the impact of that changes regarding the technology itself through the cuts, growing, also to have the impurity, because if we are talking about high efficiency cell, we have to look into what's composes the wafer. We're gonna need a certain level of purity and of the wafer, so the pullers have to be maybe much more sophisticated, or have to really reduce the processes, which also control somehow the throughput. The throughput, one of the questions that has been already mentioned by Carsten, that the throughput, which is also one of the key issue. If we consider, for instance, when we go bigger, whether it's at the outside the pullers or at the wire, so of course we increase the surface cut, but with the time, because we increase also the time of cutting, we increase the diameter of the ingot, but also we increase the processing time of the ingot, and so on. For the cell, also, how are we going to cope and to secure uniformity of the cell, of the depositions, of just sintering, for instance, after the how to call it, the screen printing, the sintering. If we go bigger and thinner, there are some stress, and we should not forget the warpage of the thin wafer. Which is also an issue, or the bowing of the wafers. So a lot of things and a lot of challenges. It's very exciting, but I'm pretty sure that through the difficulty, we manage the opportunities. I think that we're gonna move to the next speaker, because it's very interesting to have the link between all the presentations. We start with an updated overview from Markus, and then we went into the changes on the wafer size, and we saw now from large to thin, and now we will continue the benefits and the risk of large format module by Dr. Lee. So please, Dr. Lee, the floor is yours. Hello, Dr. Lee. Hello. Hello, Dr. Lee. Hello. Hello, Dr. Lee. Maybe Benjamin, can you help Dr. Lee to fix the problem? I don't know exactly what's going on.
It looks like he was disconnected.
Yes, it seems he has disconnected here. Let me try to find him. Apologies, perhaps we move on first. Let me try to find Dr. Lee. Apologies for that.
It's no problem, no problem. This is always the mystery of internet.
Yes, he just mentioned that the internet was not stable in China for the moment. Let me see. He's connecting in the moment.
He's back. He's back. He's now on screen. Dr. Lee, the floor is yours.
Yeah, let me share the screen. Okay.
Perfect. You can go ahead.
My topic is the benefits and risk. Yeah. Can you hear me? Can you hear me? Hello?
Yes, we can hear you. We can hear. Yeah, please continue, Dr. Lee.
My topic is benefits and risks of large format models. and I'm Li Shaotang from Longi Solar. So let's begin with the significance of developing high power module. The ultra high power module is developed to reduce the LCOE of power plants. The total value should be positive when making comprehensive evaluation. Reduce module cost or reduce BOS cost, and we should at the same time ensure the module reliability and the compatibility. So we think it's not correct that the larger module size, the better. It should be the optimal module size can have the best value and control the risks. So next, I'll show you the 3 approaches to increasing module power. One is using the high efficient cell. The PERC cell will in recent years replace the BSF monocell, and the efficiency of the PERC cell grows from 21% to 23%. And in the module process, we use half-cut technology, MBB technology, coated glass and white EVA. That's the new material for module. And to further increase module power, in 2018, the industry began to think about increasing module power by increasing the size of modules, either by increasing the cell area or increase the cell number. So we think about the module and the wafer size. Is it reasonable to unity PV and semiconductor silicon wafer? We don't think so. The semiconductor wafer the size of the semiconductor wafer will not affect the chip package process and the application terminal. But for the PV industry, the PV wafer size will affect the PV cell size and also the module size, and the PV plant will be the design of the PV plant will be changed if we increase the module size a lot. For the semiconductor industry, the chip process is the most costly, but for PV industry, the cell cost only accounts for 7% of the PV system cost. So the cell manufacturer cost is not the key factor of the PV industry, but we should consider more about the PV module and the PV power plant. So let me tell you why we launched the M6 standardized module. In response to the mixture application of multiple wafer size after 2018, like the G1 wafer, the M4 wafer, and so on, Longi launched the M6 standardized wafer and the module because it can realize the full thing replacements of the M2 products. The module size is slightly increased by 4 to 5%, like the photo below. It's either in rooftop, like residential rooftop and the C&I, also the utility PV plant. The M6 can replace M2 module in all these things. And another, we utilize the equipment merging, but mostly consider about the cell production. And also utilize the merging of the glass wedges of the module, so we can reduce the manufacturing cost. You know, the capacity of the glass may be with the wedges of 1,050 millimeter will be more than 100 gigawatts. So the cumulative shipment for the LONGi M6 module have reached 10 gigawatts in 1 year. So if we slightly increase the module size, so that means it's not affect the boundary conditions for PV station design. The BOS cost will be reduced. Like when the power increased by 2%, the BOS per watt can be saved about 0.14 cents per watt. But if we increasing the cell number, it brings limited value. We should increase the string power. So the cost of mounting system and the pile foundation will be saved. Then I'll tell you why we chose M10. We think it is the optimal site with systematic consideration, like production feasibility and cost, include industry chain cost, manufacturing yield, material supply, like the glass, and the module efficiency. And then the module reliability, like mechanical load, hot spot, and the junction box, and the system compatibility, like if it can be used in mounting things and compatible with the tracking system and the cable. And then the module transportation, it should be considered about the height of the container and the transport reliability and the security for the workers, and the manual installations, like the installation efficiency. So after these analysis, we believe that the increase of size should stop at the M10. The module area about 2.561 should be less than 33 kilogram. The power of the PERC module will be about 540 watts. Further innovation should focus back on the improvement of efficiency and power generation. So let's see the cost. About the wafer, the G12 wafer will increase the cost because the wafer will be wafer thickness will increase, and the slice yield will decrease several percentage. But in the cell process, G12 will save the cost by 0.0% per watt. So combine the wafer and the cell process, the total cost will be the same. Or the G12, the cost of the G12 will be more will be higher than the M10 wafer, and the cell. But in the module process, the increase of the frame cost will increase, and the high current junction box, the cost of the high current junction box will be higher. So further increase the module size and the wafer size will not bring value the cost of the module. Then we let me see. Let we talk about the shipment feasibility. It will be limited by the the height of the door. So the module width is determined by the door height of the container. The width should be about 1,130 millimeter. So that's why we use we launched the M10. Yes, if we package the module like the left and the right photos, the risk will increase. And it will be dangerous for the workers to open the package. And then the module reliability about the junction box. If the ISC grows to more than 15 ampere, the current for the junction box should at least be 30 ampere, and this junction box is not matter now. And for the M10 bifacial module, the junction the 25 ampere junction box is okay, and Longi launched the junction box with a single diode. And for the mechanical load, larger area of module will bring higher deformation of module and higher shear stress. So if the module area is 3 square meter, the deformation under static load will be 40 millimeter. So there will be a lot of macro cracks, and the power degradation will be around 5%. That will be bad for the LCOE. And then I'll tell you about the bill as cost. Why big module will save the racking cost or the bracket cost? That's because we design bigger bracket like this. If the bracket carry one string, it's like this, or two string like the photo below. One pile foundation will be saved, and the bill as cost will decrease. And like the right photo, if the width of the bracket is from 4 meter to 45 meter, the cost of the bracket per watt will also decrease. So it's not because the larger module, but the larger bracket saving the cost of the mounting system. So I'll give you a design for the bigger mounting system. The length of the bracket will be around 120. The 8 string of the M10 module will be on one bracket. So you can see the cost of the bracket will be like the same, and the the M10, the cost for M10 module will be the lowest because one of the lowest because it's high efficiency. And also the tracking system, the length of the tracker will be limited to about 100 meters. So if we use the M10 module, 3 strings will be on one tracker, but the G12 module, it will be 2 strings. So the most power capacity on one tracker is more. It will be higher for M10 module. So the cost will not be the larger the better. And then the cost for electrical equipment. If we use 4 square millimeter PV cables, the cost the cable cost will decrease when the current increase, but the ohmic loss for the ohmic loss will the cost for ohmic loss will be increased. So there is an optimal point is about 14 to 15 ampere. That's the current for the bifacial M10 module. So we also can use the 6 square millimeter cables for the G12 module, but it will not save the cost for the cables. And for the string inverter, we can still use the exist string inverter for M10 modules. And for the new string inverter to comparable to the 20 ampere module, it will not further increase the DC AC ratio compared with the M10 module. And then the labor cost. The width of the module should be not very high, because it will cause the difficulty for the module to install. And let's see the weight. The maximum weight for one person to carry should be between 20 kilometer to 25 kilometer. Like in American, they think the weight for one person should be not beyond 50 pounds. And the extreme weight for two person should be 25 multiply 2 and multiply the factor is 0.666. So the extreme weight should be about 33.3 kilogram for two person to install the module conveniently. So you can see the M6 module is the best for it's just in the limitation. Then the longest Hanwha module. We chose the optimal module size, and the wafer size determined by the module size. It's about 2,256 length, and the width for 1,133 millimeter, and it's with the classical 72 cells and with half cell design. And in HAMO 5, we introduced the smart soldering technology. That means we use the integrated segmented ribbons. By using this technology, the module efficiency will increase by 0.3% compared with the conventional MBB products. The triangular section will maximize the use of sunlight, and the flex section will achieve dense soldering with low stress, so will not suffering from the risks of macro cracks. So the macro gap is 0.6 millimeter. That's the best combination of high efficiency, reliability, and cost. So the HAMO 5 and HAMO 4, that means the M6 module and the M10 module will continue to coexist, because we use the module size for HAMO 4 is the optimal size for residential application, and also the PV station with mountain terrain like this. The length of the bracket will be limited to be about 15 meter. So if we use a larger module, it will be not suitable for this terrain and hard to carry the module. And for HAMO 5, it should be used for the ultra large scale power station. For the flat terrain, the bracket can be designed to about 150 meters. So the cost will be saved by larger by large mounting system, and the electrical cost will be saved by the optimal current, about 15 ampere. So that's the photos about of the HAMO 5, the ER image, and the transportation, the installation, and the PV station. The total shipments for LONGi's HAMO 5 is 3 gigawatts now, and maybe in this year the shipment will be near 20 gigawatts. So let me conclude my presentation. For large-scale PV power station, increase the power of PV module by increase the wafer area is to a certain extent is beneficial to the reduction of BOS costs and LCOE. But the size of module is not the bigger, the better. It is necessary to comprehensively consider the condition of manufacturing and the manual installation. The M10 module with the 72 cells is the optimal module design for large-scale PV station for flat terrain. So that's my presentation. Thank you.
Thank you, Dr. Lee, for that. I would say bring us to the reality with the numbers, because all in one we can talk about large wafer. We increase the power in the modules from 300 to 400, 600, and even 700. There are some companies who are now. I don't think, but all in one, how much is gonna cost and how much is gonna generate the LCOE, because this is the key point and the key issue for the solar sector to continue its progress and to continue its competitiveness, even if the competitiveness is reached already. I would like to continue right away with Gaëtan Masson. That he's going to give us his point of view regarding the challenges and the opportunity from the upstream to the downstream. So please, Gaëtan, the floor is yours.
Thank you, Nabih. Do you hear me properly?
Yes.
I assume so. I will try to summarize a little bit what has been presented today. I think we had quite an interesting set of presentations going in different directions. Just would like to, if I can change slides. Just a second. Just saying a few words about my company, Becquerel Institute, who's co-organizing with SOLARUNITED this event. We are a company specialized in photovoltaics for 7 years, established in Brussels, but active on all continents, and providing strategic and market analysis for PV companies and other stakeholders. I'm coming back to what has been presented by Markus Fischer earlier, and it's something is quite interesting is simply the fact that for years we haven't seen many change in wafer size, and since 2016 and even more since 2019, we start to see changes which, as we have seen, might have a significant impact on many stakeholders in the PV value chain, with significant changes in wafer size. And that's where we are for the time being, and the consequences can be quite interesting. I would like to remind you that the Chinese Photovoltaic Industry Association in February announced forecasts for wafer sizes, which I'm going to present now. As a reminder, non-Chinese share of wafers, including Norsun, which we have seen, and a few others, is below 4%. So we can, to a certain extent, believe what CPIA is telling us when they are telling us that this year, 45% of the market would be either M10 or M12, and that's in 2023. These two wafer size could go up to 80%, and from 2025, which is only 4 years from now, about 95%. Which is even more interesting is that until that date, until 2025, they believe that M10 would be in equal share with M12, and then after that, M12 could grow. And I'm not going to take any stance. I think the arguments presented by LONGi are quite smart and sensitive. But we also know that sometimes industrial aspects are changing the market faster than logic. And we have two consortiums of companies which have been formed, one in June 2020 with 8 companies calling for standardization around M12 wafers. And in November 2020, 7 other companies, including some of the ones also signing the M12 wafer consortium, went for M10. So there is absolutely no consensus in the industry, and we still have actors believing that we could stay with M6 and
Gaëtan, there is some noise. There's some noise coming from when you speak.
It's weird because it's totally quiet here, so it might be some. Is it still the case?
Yes. When you talk, there is a noise.
I'm sorry. Can be my. I can try without headsets. Let's see if it's better, but I'm not sure. Is it better like that?
Continue.
I can try to continue like this, but I will be short in any case.
Okay.
I've extracted that figure from a presentation from our Japanese friends from RTS Corporation, showing that the number of high efficiency modules which are being put on the market for the time being are really going in the direction of either M10 or M12 or even G12 in some cases, which indicates that the trend is going pretty fast. And what was hard to foresee 2 years ago is becoming now a trend. And in any case, this is something that will happen, as I was saying in the beginning, when you have actors representing more than 90% of wafer productions in the world telling us that we will go for either M10 or M12. Most probably, this is something that will happen much faster than what we expected. We did a little exercise at Becquerel Institute trying to see what could be the impact on MCOE, and then we conclude slightly the same thing as LONGi finally, is that M10 allows indeed to reduce significantly I would say if we take the case of Germany for a 10 megawatt plant with a capex of 0.5 euro per watt peak, monophasian, no trackers, and other, I would say, conventional parameters. We see that going to M10 can reduce up to, I would say, 0.02 cents the LCOE. If we go to M12, it's far from being evident, and we can say that in the best case, we can even slightly increase the LCOE. If we do the same exercise for the PV plant in Spain, we see that the reduction is the same order of magnitude, so there is an interest in increasing them from, I would say, installation point of view, but going above M10 quite complex and doesn't give any significant improvement. But in my opinion, it's even more important is which are the possible impacts on the value chain in general, because changing the size of wafers, as some of the speakers mentioned, can have significant impact at different levels. I will not go through all of them, but it's clear that R&D centers will have to invest massively if they want to continue. That equipment manufacturers will have to upgrade the products they are selling. Tools will need to be changed for cells and in many cases for module manufacturers. So most probably it will impact the entire PV value chain by accelerating the consolidation, which hasn't been that fast in the last years. So we might see many equipment manufacturers and many small and medium-sized cells and module producers being unable to follow the path, even if they have to select between M10 and M12 in the coming years. So this might be the most interesting summary of what's happening now. And it's for companies what to do, what kind of technology to adopt, what kind of wafer size, or to transform that into models which might be competitive, and at the end, when to do it. It's the first technology game changer that we really see in a decade, and it's something which will have extremely important consequences, in my opinion, in the years to come. There is an impact on LCOE, so it makes it attractive for developers and especially for extreme. So I have little doubt that it will develop. It will develop massively and very fast. It will put pressure on manufacturers staying with current wafer sizes to also upgrade, with the consequences that it can have for smaller producers with the necessity to change the equipment, change module size, and for some specific niche, I'm thinking about BIPV, for instance, it's no good news because half-cut cells are not really suitable for aesthetic BIPV. You will tell me maybe in some cases. So we might still see a market for, I would say, smaller cells based on smaller wafers, but most probably it will remain a niche market. The impact on equipment manufacturers, as I will say, will be quite important on research centers as well, because there is a need for a new investment cycle. And I remind you that in the semiconductor industry, a change in wafer size happened a certain number of years ago, and it led to a major consolidation. So it's not something new that's never happened in the industry before. It's something which is relatively new for PV, but we can look at what happened in other industries to figure out what might happen here. There is a need for standardization, that's for sure. Honestly, I think it's extremely difficult for the time being to see in which direction we will go. I would tend personally to agree with Longi about the fact that M10 on the short term is probably the best solution. But on the longer term, I would say after 2024, 2025, it's not easy. And then it has been mentioned by Carsten Rohr from Norsun, there might be some question of bankability. Not only about cutting cells, but about mechanical resistance and about many changes which can impact quality and reliability. So we will most probably see in the coming years some interesting questions coming about it. And then I will finish about that, I think the question is not whether upgrading and changing, but when and towards what. And it will be a key question for plenty of actors in the coming months and years. And I think it will be really the beginning of a, I would say, shaky period for many PV actors, whatever their size, because the choice made might have long-lasting consequences. I will finish by saying that there will be a Solar Industry Forum event at the UPV-SEC this year, where, of course, we will discuss the question of larger wafers and the consequences on wafers, about new cell technologies, new module technologies, and other aspects. And I would like to thank all organizers, especially my man, but also Markus for the organization. Thank you very much.
Thank you, Gaiton, but it was, the sound was not very clear. It was noisy. But anyway, I think that we all understood your message and your presentation. I think even if the time is over, I would like to ask maybe one question each, because they are burning my lips, and I'm pretty sure that others behind their screen, they are also thinking about some questions. So maybe one question to Carsten, please, because we are talking about big wafers, and also at the same time we talk about the thickness of the wafers, and we talk about the throughput and the gram per watt that we're going to generate. What do you think will be the trade-off between large wafer, thin wafer, and the curve loss? Do you see, for instance, for the industry to make another move through that large wafer to something that we call it curveless, like for the direct wafer from this the company 1366, or the process that has been developed by Hanwha, and now it's Nextwafer wafering. What is your opinion, please?
Yeah, those curveless technologies, that the increase in wafer size doesn't make it easier, of course, and so that will be interesting to see how they can commercialize their activities. So it remains to be seen how well that works. But I think in principle, as I mentioned, there is an opportunity for going thinner before going larger for certain technologies that are more suitable for that. So that's certainly an opportunity. You're on mute.
Yeah. Thank you for your quick and short answer, and a very clear answer regarding that matter. I would jump also to in the same way to Anis, and regarding the thickness. And we all know, and you show it also somehow, that for instance the heterojunction technology and the beauty of that it can handle a very thin wafers. So now going big, and how can we, I would say, move with the heterojunction, and also, and do you see a motor drive for the heterojunction technology to be developed, to be, I would say, implemented faster through that move to the large wafer, because it's going to need for several companies to change their equipment and their production line. What is your opinion on that? Hello, Anis. Hello, Anis. Maybe he's not. We can't hear you, Anis. Okay, if Anis is not with us, I would like to ask not exactly the same question, but something similar to Dr. Lee. And we know that LONGi is, I would say, production is mono-PERC. And do you see any move for LONGi to another technology, and implementing larger wafer and a bigger size modules?
Yeah, we think we have found the optimal module size, and the advanced cell technology is in R&D, and I think we will launch the new module with the new cell technology this year. Maybe the module efficiency will exceed 22% next year.
That's great. That's great. And you know that in 10 years, I think that we went from 14% of module efficiency to now over 20% in 10 years, which is extremely incredible improvement.
Yeah. That's very important for LONGi to make cost-effective cells. So the module cost will not be very high, and the LCOE of the new product will be better than the PERC cell, PERC module.
Okay, and how do you see, I would say, the industry, not only LONGi, establish itself from now on in terms of the new technologies?
Yeah, I think LONGi will keep innovation to lead the innovation of the whole industry. Yeah, like the PERC and the bifacial PERC module and the module side.
Carsten and Gaëtan, both of them, they mentioned about the bankability. Did you face any question about the bankability of a large module? Can you hear me? Hello? Can you hear me?
Do you ask me? Or?
Yes.
Oh,
yes.
oh.
I asked you because I said that Carsten and Gaëtan, they mentioned about the bankability of a large module. Okay, yeah. And as you already you mentioned that you already export last year about 3 gigawatt of these large modules. Did you face any bankability issue, or these modules were the bankability were not a request?
No, not yet. I think LONGi is the most bankable company. Our customer trust LONGi.
And all this 3 gigawatt was installed in China or elsewhere also?
Mostly China.
Mostly China.
Because the other countries will need the Chinese project will be very recently for the order for other countries will be 10 months. 6 will need a time about 6 months. So there is also some shipment to the other countries.
Okay, so thank you very much, Dr. Lee. I think that we already overpassed the time and we have to conclude. I would like really to thank all our speakers for the excellent presentations and the excellent input they give to us regarding the new trend, and that's real, I would say, big jump in about a year and a half, in spite of all what's the world lived for this pandemic and all these things. We saw that the industry and the solar industry made a huge jump from what we call it, I would say, the classical, I would say, M2, which is 6-inch wafers, to now talking about even 12-inch or M12 M12 wafers in a very short period of time. And I think that the future is really very bright for that industry, which is still at its infancy stage. The development that we are witnessing, and we already witnessed since, I would say, the solar photovoltaic to be deployed worldwide, is incredible and unprecedented. And it's still a lot to come, especially now, and it will be a very good excitement when we're gonna move to other technologies through the tandem or something like that. And it will be extremely interesting to see how the size is gonna be used and how these new technologies will impact the size of the wafers. So I would like again to thank you very much for your time, for your presentations, for your input. And I will take also that opportunity to thank all our audience. We had over 90 participants from all over the world. Thank you all, and we hope to see you soon in one of our webinar. SOLARUNITED will be organized with Becker Institute, will organize more and more, and would like the webinar, and all these webinar will be also, as they are recorded, we'll have them posted in our website, and we invite all of you to check our website and to to give us all your input, your recommendations of what, or your suggestion, if any topics of interest to you, whatever. And thank you very much all, and I give the floor to Brian.
Thank you from Longji.
Yeah, thank you, everybody. It's been a pleasure. Nabih, thank you for moderating today's session. And thanks again to our panelists for the great presentations. It was very good. As Nabih mentioned, these will all be available very soon on the Solar United website, as well as the Becquerel Institute website as well. And as Gaetan was mentioning, we will be organizing another much bigger event at the EU PVSec, which will be the bigger solar industry forum, and more information will be coming out on that very soon. So thanks again, and I wish you all a very good day wherever you are, and we'll see you all again very soon. Bye-bye.
Thank you. Bye.
Bye-bye.
Bye.
Bye-bye.